Good morning. Now we'll see about how to design a IIR filter. Okay, so whenever we want to design a IIR analog filter, okay, whenever I want to design a IIR analog filter, these are the steps we have to follow. First step, identify what are the specifications given in your as per the thing. Okay, so first identify from the question what are the specifications required. Specifications, what I mean by specifications are what is the passband attenuation, what is the stop band attenuation, what is the passband frequency, what is the stop band frequency. These specifications we have to identify from the question. Second, once you know these specifications, we have to find the order of the filter. So we have to find the order of the filter. Okay, that is a specific formula. By using that, you can find the order of the filter. Okay, once you found that order, you need to round off. Okay, round off to the next highest integer. Next highest integer. Okay, we'll see this when we actually go into the design. We have to round off to the next highest integer. Okay, so based on this based on this order, okay, the fourth step is you have to find the transfer function h of s. Okay, for you are going to find a normalized transfer function for a cutoff frequency of 1 radians per second. We'll find a normalized transfer function for the given value of order. For the value of n, you find h of s for omega c equal to 1. Okay, that's how the first step. Then you calculate the actual cutoff frequency. You calculate the actual cutoff frequency. Okay, you will be calculating the actual cutoff frequency. Then what we'll do is this original transfer function which we have created using omega c equal to 1, no, in that we have to apply wherever s is there, that s you have to replace by s by omega c. This omega c we have calculated here. Okay, we will calculate the actual cutoff frequency, that is omega c. Then wherever in your h of s you have s, you have to replace the s by omega c. Now this transfer function or this filter equation is working for that particular cutoff frequency. Okay, idea is first you design it for a nominal cutoff frequency or a normalized cutoff frequency of 1 radians per second for the given order. Then you convert that into our transfer function as per our required criterion. Okay, so that is the rule we have to follow. Okay, now we'll see how to design using or the first step. The first step is the specifications and the order. We'll see this one. Okay, so particularly we are concerned about there are two types of design as well as IIR is concerned. One is Butterworth, second one is Chebyshev. So first we'll start with a Butterworth filter. Okay, a Butterworth filter, and first I'll just put the formulas so that you will identify what is it. Okay, so to find the order of the filter, okay, so first I'll draw a low frequency LPS filter. Okay, so for this low pass filter we are actually specifying a lot of terms. One is omega p, pass band frequency. Second one is stop band frequency, and this particular region is called as pass band attenuation, and this one is called as stop band attenuation. Apart from this, you have two more parameters. This particular point is given by 1 by epsilon square, and this is given by 1 plus lambda square. Okay, so these two parameters are very important for you to understand. So here it is 1 by 1 plus epsilon square, and here is 1 by 1 plus lambda square. Okay, now we define the order of the filter formula for Butterworth. Order of the filter should be greater than or equal to log of, okay, square root of 10 power 0.1 alpha s minus 1 by 10 power 0.1 alpha p minus 1 divided by log of omega s by omega p. Okay, this is how you define your n. Okay, and interestingly here you should note that this 10 power 0.1, this value, okay, is nothing but epsilon. You can put epsilon is equal to square root of 10 power 0.1 alpha p minus 1. Similarly, lambda is equal to square root of 10 power 0.1 alpha s minus 1. So our formula essentially transforms as n is greater than or equal to, since this is lambda, this is epsilon, okay, we can put it as log of lambda by epsilon by log of omega s by omega p. Okay, this is how the order formula actually transforms. Okay, we'll see with a small example. For example, we'll see one example to find the order of the filter. Okay, so say omega p is given as 1 decibels and omega s is given as 30 decibels, and similarly the passband sorry, this is I mentioned it wrong. This is not omega p, this is alpha p. Alpha p is 1 decibels and alpha s is 30 decibels. Okay, so whenever they give higher decibel value, that indicates the stop band attenuation. Okay, similarly the cutoff frequency is given as 200 radian per second and omega s is equal to 600 radians per second. Okay, now it is just a substitution of the direct one. What is the formula for n? N is log of square root of 10 power 0.1 alpha s minus 1 by 10 power 0.1 alpha p minus 1 by log of omega s by omega p. So if you substitute, okay, if you substitute, what I am getting? Log of square root of 10 power alpha s is 30 into 0.1, 3 minus 1 by 10 power 0.1 minus 1 by log of what will be getting here, omega s by omega p. So 600 by 200. So if you solve this, n should be greater than or equal to log of 62.115 by log of 3, so which comes to 3.755. so n should be greater than 3.75 or n equal to 4. Okay, so this is how you fix the order of a filter.